Okay. Um, Hello, we're the implementation of object detection in FPGA group. My name is Shivansh, and this summer I worked with Shivam, Aayushi, and Vrishin. Unfortunately, Aayushi won't be speaking today because she's coming down with a throat infection. Um, our goals for this project were as follows. We wanted to start off by learning about object detection, and also we wanted to see how machine learning works in relation to our project. And lastly, we wanted to implement object detection on an FPGA for faster detection. So what is an FPGA? An FPGA is short for Field Programmable Gate Array, and these boards are semiconductor devices with programmable logic blocks. An FPGA enables users to program features and functions and adapt to new standards at any time, and you can reconfigure hardware even after it is already in use. One of the benefits of using an FPGA is faster processing speed. It can run faster because it can run multiple logic blocks in parallel and run more tasks at once. But to achieve this, the FPGA requires more energy consumption. So that's one of the major drawbacks. There are many different types of FPGA boards for use in the market, and they have various applications. But the one that we use for this project is the Xilinx FPGA's Alveo U200 accelerated card, which can be seen in the top right of the slide. This FPGA plugs in similarly like a GPU, and the cards are inserted directly into the nodes in the Orbit sandbox, and we were able to access them remotely to run tests on them. The second image is a simplification of how the chip actually looks like, where the outputs can leave one logic block and enter another logic block input. Yeah.
FPGAs are different from the standard CPUs that control your computers at home because they don't contain layers of abstraction on top of them. This means you can talk directly to the chip and code closely to it and make it do exactly what you want. This requires the use of a hardware description language. Xilinx uses a language called Verilog, and that's made up of modules that have inputs and outputs. The physical representation of these modules would be the logic blocks you saw in the previous slide and are modeled in the picture with a simple AND gate. We are able to take these inputs and manipulate them to give us an output that we want. Next slide, please. What we wanted to discover for this internship was how object detection really works. For us to attempt to implement it into an FPGA, we needed to know the software side really well. For detection, images are fed through a neural network which has multiple layers. Each layer manipulates the data based on an algorithm and results in an output of where we can find out where to graph bounding boxes around the detected object. The speed of this process is decided by how fast our hardware can finish one image. Processing video requires taking time in each frame of video and passing it through the neural network. Next slide, please. The algorithm that we chose for our object detection was YOLO3, which stands for You Only Look Once. Compared to our other choices, this one was really fast and accurate. And with OpenCV and Python, we can upload the YOLO3 configurations and weights into the built-in deep neural network, and we use the build-in function to input, parse outputs, and run forward passes on the data to accurately detect objects. Accuracy is determined based on the resolution of the YOLO3 configuration that we use. We use the 416 by 416 area, which balances accuracy and keeping the data size low for faster computing. With faster processing, we can increase the accuracy and by increasing the input resolution. Next slide.
So for testing on a CPU. So initially what we wanted to do was get more familiar with machine learning and how we can use it in our project, and that would be object detection. So instead of jumping straight into putting it onto the FPGA, we kind of needed to know a little bit about it in the background. So that's why we wrote our Python script with YOLO v3 implementation. So the main thing that we used was OpenCV, and it is a import that you can utilize its deep neural network, which is DNN. So what we were able to do is YOLO v3 provides us with a weights file and a configuration file. So we can upload those files directly, and then it will allow us to use YOLO v3 in our program. So what we were able to do is take images from a video, whether we were doing a live webcam or whether we were inputting images one by one with OpenCV. And what we did is take it from that input image and then convert it to a blob and then run that through the deep neural network. And that takes care of most of the heavy work for us. And from there, we're able to just take out the output data, which gives us the classification of the image. It gives us the bounding box information, and it gives us the size of the bounding box. So we're able to graph on each frame the bounding box size, where it's located. We can show accuracy of how confident the computer is in thinking that that object is that object, and we're able to classify it like that. Next slide. So this is the video with our program. So this is running on a CPU. So this would be one of the slowest applications. So as you can see in the top left corner, it gives us the frame rate that we're running at, which is 3 frames per second. So this is quite slow. And for any real world application, this would not be sufficient. But you can see that it is detecting objects, and the accuracy is pretty good, where it's getting between like 88 and 95% accuracy for most of the objects. But it would not work in a real world situation because we're not running at this slow of a rate. So this is why we need to explore faster methods of doing object detection. So if you go to the next slide. So what we were able to do here was use a GPU that I had, which was a 1070 Ti that has a lot more processing power than a CPU because we can use it dedicated for one task. And that's what we did here. So you can see the improvement with the frames per second is about 18 to 20 frames I was able to get. And you can see how much faster everything is moving and the more real-time detection. You can go to the next slide. So difference in hardware. So we learned about neural networks in a language we know to apply to FPGA implementation. So by using the Python and exploring and figuring out how to use it there, we can apply that to trying to implement it on the FPGA, which is a much harder task. So CPU versus GPU. We compiled the program using OpenCV for GPU, and we were able to see that speed improvement right there. So we wanted to take that information and see how it translates with the FPGA and how much faster we can get with that. And we were able to see a 6 to 7 times difference in the speed. Next slide. So implementing on an FPGA. So initially this task was actually pretty hard. There's not that much information out there for like researching besides just reading up on the manuals and documentation that the FPGA comes with, especially for the Alveo card because it is a very advanced FPGA. So it was hard to directly implement, where it's not where we can just write a script and upload it and call it a day. It's a lot more complicated because we don't have that layer in between our processor and us that takes care of all the heavy work. So we have to learn about that and implement it that way. So the main usage for our specific card, which was the U200, was using Vitis AI, which is an artificial intelligence and machine learning library that helps us communicate with the card. And it's run all through terminal. So we were able to do it right on the node in Sandbox 9. So it's a high-level development environment for machine learning applications, and it contains a lot of libraries and tools that you can compile on premises and deploy that way. And it also includes YOLO v3 implementation capabilities. Next slide. So the Vitis AI library is one of the tools that was inside that GitHub repository. So it has a lot of pre-trained models that you can deploy directly, and you can compile and quantize those models. I'll explain the quantization later, but we were able to run YOLO v3 on the FPGA, and this was single image, so we weren't able to get video going just yet. We ran out of time, but what we were able to achieve was about 17 to 20 milliseconds per image. So if you translate that up to a video, it's around 50 to 60 frames per second, which is almost double to triple what we were able to get on the graphics card, which was really promising news, and about 20 times faster than the CPU. So the graphic on the right you can see is from Xilinx's website, showing like for certain machine learning applications, how fast these different hardwares can go through images. So you can see the first two in the blue are CPUs, and then you have the NVIDIA V100, which was also on the nodes that we were using. And then you can see the two Xilinx cards. The one that we specifically had was the U200, which is the second, is the first red one. And it's about 2 to 3 times as fast as the NVIDIA graphics card. Next slide. I just wanted to say thanks to Professor Yuan for helping us and guiding us through this project. Does anyone have any questions?